Who we are. My name is Anton. I work at Popularium. It's a game developing company. And I'm in charge of data science activities there.
Right, and my name is Vladimir. I work at SteppeChange. It's kind of a data science shop, and I happily indulge in data science and data engineering activities there. So
we're going to cover, as you may notice, there are two of us, and there will be two parts of the talk. And first part will be about application of deep learning to real business problem. I'll try to explain how deep learning may be helpful for almost any company in almost any business domain. And the second part is about making deep learning distributed.
Right. Click. Right, and a short slide about why we're doing this. So at work, we sometimes have problems which really could fit well for deep learning kind of stuff. And we always have debates. If it's going to work fast, should we use that? Because it usually takes a lot of time to train the model of this kind. And we never know because we never have time to test actually what's going to be the fast way to do that. And we decided to try it out now and report results to you, obviously. And that's what we have for you here. So that's why we have two parts where we just select one model, right, to test it, and then we test it. And Python, relation to Python, right? So this is Python conference, obviously, but our talk is more like about deep learning. But anyway, we use a lot of frameworks which are pure Python. Of course, on the backend, they have a lot of other types of code, but still, all the APIs we use are Python-based, so you can also check that out and play with the code. Right.
So let's start with the first part. It will be about modeling, and I'm going to go a little bit further, encouraging you to use deep learning, to use Tensorflow or other deep learning frameworks for your problems, and we'll try to explain how it actually can be useful. And this part will be rather introductory and general. So if you are a guru of deep learning or machine learning, excuse me. First thing, let's start with motivation. Some of you may say, so I work in a software company, in bank, in a gaming company. We don't have any voice assistants, no robotic cars, no AI Go players. Why do I care? Do I really need deep learning? And one of the examples is churn prediction. Churn prediction is a topic that is relevant for almost any company and is relevant for almost any business domain. What is churn prediction? Churn prediction, it's when you try to detect customers who are about to leave. And these red guys are pretty frustrating, and you want to catch them halfway when they just start to turn red, and make them change their mind. Just that easy. There are two types of churn. First type is contractual, when your customer explicitly says that he or she is going to leave. And the second type is non-contractual, when your customer just silently stops using your services and stops paying you, and the life is that non-contractual churn is more common. That's why we stick to it. Let's take a look at basic definition of churn problem. This is very simple definition and very rough, but it's kind of universal for many industries, and we stick to it. So you have your customers. Customers visit your website or buy your products, and you see these events like blue crossings here. And you have a fixed period. I call it target definition period. When you track your customers, if your customer came during this period, then you assume that this customer is active. If not, then he's left, and you mark it as ones. So The problem is quite standard, and some of you may say that, come on, I don't need any neural nets, any deep neural nets with their thousands and millions of parameters. I have a bunch of tools like logistic regression, like boosting, like something else, and it's just a binary classification, come on. So, in order to use this classical approach, you have to have your data in this flat table, where you have your customers row-wise, and where you have different characteristics of your customers, we call them features, in columns, and you have your last column with the target. And many experienced guys would say boosting should be your first step, just try it, and most probably you'll get what you need. For those of you who don't know what it is, boosting is just a combination of weak algorithms, typically decision trees, and you build next tree to fix errors of the previous one. Just this simple idea, and it turned out that this simple approach, ensembling these simple trees, indeed solves many problems, solves it well. And let's stick to, for example, boosting, and you just have to have your data in this flat table. Typically, in your production system, you have data in transactional format. You just have, for example, customer IDs, timestamps of their actions. You have different types of actions. You have different values associated with these actions. And in order to turn it to the flat table, you just have to do some data transformation. Typical way is just to take some aggregation functions like sum, count, count distinct, min, max, and you aggregate your, for example, visits, purchases, refunds, bottles for some aggregation periods like 1 day, 3 day, x days. At this point of time, you start thinking that maybe the number of columns is going to be high. And next thing, you want to add some dynamics. You want to express some dynamics in your data set. So you just step back for 1 day, and you calculate all the metrics as of this date. You do the same with log 3 days, x days, and so on. And at this point of time, you clearly see that the number of columns grows exponentially. And for example, if you have 50 event types, 5 aggregation functions, 10 aggregation periods, and 10 logs, you have 25,000 columns, and it's quite big. How we could avoid this combinatorial explosion? We need something different. We need a model that would accept time series sequences as an input, and tada, deep learning goes on stage. With special kind of deep learning, you can shrink the number of columns you have to 2.5 in this example. So let's finally talk about deep learning. Deep learning, deep neural net is just a neural net that has more than one hidden layer. And there is a special type of deep neural network. It's called recurrent neural network, or RNN, and it was made specifically for accepting sequences as an input and for holding memory about the previous states, previous values in these sequences. And you may think of it, so the recurrent neural net has a loop in a hidden layer, and you may think of it as just a sequence of ordinary neural nets following one another. It turned out that recurrent neural nets that were invented in 1980s, it has problems with memory, actually. And that's why RNNs weren't widely used for almost 30 years. But the new architecture called LSTM, long short-term memory, was invented in 1997. And 10 years later, it really revolutionized many areas like speech recognition, like natural language processing, and you may heard that Google Translation, Google Translate service recently switched to RNNs, and that was thanks to LSTM. And GRU, it's a gated recurrent unit. It's just a recent simplification of LSTM. It has less parameters and performs, in many cases, it performs well. So we'll be using GRU. A couple of words about technologies we'll be using. Tensorflow is an ML library from Google. I'm sure you know it. It's a very flexible and way to code your neural nets. You can run the same code on CPU, GPU, cluster of machines, and you run the same code. It supports what we need, supports LSTM and GRU. It has Python API, perfect. Keras is a high-level API in Python. It's very user-friendly. You'll see in a couple of minutes, you'll see how it's actually easy to build neural networks with Keras. It runs on top of TensorFlow, Theano, and some other frameworks. So we know theoretically that deep learning can be of help for our task, and let's move to practical example. As I already said, I work at Poговорим. We try to deliver world-best gaming experience to our players, and Vikings, War of Clans, is one of our most popular MMOs. It's a mobile and browser MMO. So users has huge variety of actions in this game. You can create clans, you can train troops, obtain resources, attack other players. You have social interactions, competitions, tons of data. And besides that, gaming actually helped deep learning in some sense. It turned out that GPUs that were initially developed for gaming are well suited also for deep learning. And it's now its turn of deep learning to help gaming. So we've built a data set. We have 3 months of data as an input from May to end of July. 1st of August is our calculation point where we stay and make predictions. Churn definition period is 3 weeks. In August, if customer made less than 2 sessions for the first 3 weeks, then he left. If not, it's an active customer. We also filtered out all the newcomers to have at least 2 full gaming history, 2 full weeks of gaming history. And also we filtered out just casual players who played less than 7 game days, just to have really people who played the game. And also we filtered out people who have less than 1 session during July, assuming that they left already. The last step is take 100,000 random players, 121 feature from our feature store, and we have 9 gigabytes of data set unarchived. The network architecture is pretty simple, just an example. In neural nets, you have input, you have output, and some hidden layers in between. We use 2 RNN layers stacked one after another just to make our model more flexible and really deep. And we have a dense layer just to transform the output to the desired format. We use batch normalization just to eliminate negative effects of features of different scales. It makes the model more robust and it helps to fight overfitting. And we also use dropout to, in dropout layer, we just randomly drop out 50% of weights, of activations. And let's take a look at code. I don't include inputs here, but I import just NumPy, a couple of functions from scikit-learn, and models from Keras. Here we just load the data, split it to train and test, set parameters, number of neurons in a hidden layer, a number of features, number of days. Then we initialize our model. You see how it's simple in Keras to actually initialize, to create a model. You just sequentially initialize layer by layer. You provide it with the input shape only for the first layer, and all the other layers are input shapes for them are inferred automatically by Keras. It's very handy. And we use softmax activation to have the data in the desired format. Then we compile the model, we fit it, and we predict. That's it. And then we check the score. How it was trained. This is a chart. You see loss across all the epochs. Blue line is a loss on a training set. Orange line is loss on a test set. You see this strange spike on the 5th epoch, but it's just a kind of outlier. It happens sometimes. But in general, the model trains good, and the model performance in terms of area under curve, this is just a common measure of model performance. Catherine used the same metric. I think that you already know something about this metric. And it's 0.97, which is quite decent. About speed. Training took 16 minutes per epoch, 3 hours in total. Execution takes 1 minute for each 10,000 customers. And it's not that commodity hardware. It's 32 threads CPU. And so the model, so it's slow. We need to speed it up somehow. What we've learned so far. We know that neural networks are very flexible. They are performing. If you have time series as input, they can simplify your life a lot. They're not scary, especially with Keras, but they are demanding for resources. They are slow, and we need to somehow speed it up. And this is exactly the topic of the next part of our talk. And stay tuned. Vladimir, over to you.
Thanks. No, I think I'm going to use this one.
Okay.
Thanks. Take a seat. All right, it's a little bit. So thanks, Anton, for covering the first part. Now we have the model to optimize, right? And this is actually, the churn modeling is quite common in our business, right? So this is a real situation, and the model is pretty much real. And now we're ready to try to optimize it. So before we do that, before we jump to benchmarks and the conclusions, right, we want to know a little bit about the history, about the background, and we'll discuss the types of parallelism you can do and some frameworks you can choose. So let's get started. As you know, we live in big data era, right? And the more data we feed in a model, usually the results get better. And this holds true for even this task, which Anton has shown just now, where we had just like not even, as it's mentioned here, not even speech recognition or physics modeling, nothing like that. Just regular customers, a lot of features in the data set is still huge, has a lot of features and stuff like this. So, and all this kind of models, all this kind of problems require quite long training, right? So, and this kind of justifies the need to try to make it faster somehow. So let's try that. How do we do that? For that, we need to take a look a little bit at the history. Take a look at this guy. His name is Jeff Dean. Some of you probably know him. He works now at Google Brain Project, And at 2012, he worked as a the computer scientist, on this belief framework, which is a parent of the modern TensorFlow. And back in the day, it was used at Google for machine learning at scale, deep learning. And 2012, this year, this paper was released. It's called Large-Scale Distributed Deep Networks. It's quite well known in the community, and it's kind of remarkable, right? And in this paper, he and his colleagues at Google just discussed a few algorithms, Downpour GD and Sandblaster, which is a framework LBFGS. These two approaches for deep learning at scale. And these are asynchronous data parallelism algorithms. So what does it mean, asynchronous data parallelism? Okay, maybe some of you might guess what it is, but let's discuss it anyway, right? So on the left-hand side, you can see model parallelism. If you remember, the model which Anton has shown to you has layers, right? In the code, it's very much clear in the Keros code. So the idea behind this way of paralleling models is that we take each layer and we can assign it to different device. In TensorFlow, for those of you who know it, who use it, you know it's very easy. You just take some simple construction and you assign, for example, one layer to a CPU, another to a GPU, another to a GPU2, and stuff like this. So it's very simple, seems like, right? And you can parallel computations this way. And there is data parallelism, where you take model as it is. You don't do anything to change it. You just replicate it across different machines. And you do computations in parallel on these machines. And of course, there is a mixed approach where you do obviously data parallelism, and on each machine you parallelize the model on different devices. Let's discuss briefly model parallelism. So we discussed the idea behind it. And there is a problem with it, is that not all the types of model are easily splittable this way, because some networks have a lot of interconnections between layers, and to parallel them, like paralleling them, is going to degrade the performance of the whole training process, right? Because they have a lot of data passing between these layers. So RNNs can be parallelized this way, but still you need to know a lot about architecture, how to put it the right way so it doesn't slow down the whole training process. So it gets a little bit tricky. So we are quite lazy, right? We don't want to do that. Let's just use data parallelism. Why would we touch our model? And the problem here is that how do we synchronize all these replicas? You remember there are a lot of replicas of the models. How do we use all of them to converge one central model? This is the question. And this picture here illustrates the architecture behind the solution of this problem. So there is a PS server, parameter server, which holds all the coefficients shared by models. And model replicas are in the center, and the data shards, different data pieces are fed to model replicas. And each batch, the model gets fresh copy of params, works with them to advance on the problem, and sends the updates back to the PS server. Now the question is, how do we, again, synchronize it? Because we either can lock PS server and wait for all the batches to complete before advancing to the next one, or we could do it in a synchronous way. So we don't lock anything. So there are two approaches, synchronous versus asynchronous. Let's discuss synchronous first. It's a very simple approach, seems like, because intuitively, right? You just lock one central place and all the other instances are just waiting. It's very simple to implement, right? Unfortunately, it has some shortcomings. Imagine you have a cluster. The hardware is usually not homogeneous, right? So we have different types of machines. And it makes it, might make the performance lower because the cluster is not fully utilized. Some machines will perform worse than others, and others will stay idle, waiting for the all machines, for the all other machines, and only then the lock will be released. This is a problem, and there are few solutions to this. Like we could synchronize every nth step, like second, third, 10th, or stuff like this within some window. Or we could just disregard the results of the least performing machines. That's also a way. There are more approaches, actually. It's an active area of research. And the upsides of this approach actually is that there is no magic, right? It's kind of simple. There's just central lock, so we can set bigger learning rates, and the model is going to converge. Everything's going to be fine. And let's talk a little bit about the synchronous approach. It doesn't have those problems of synchronous approach because we don't lock central server. But instead, we get some other problems because we get this straggler problem, so-called. It's when the coefficients are stale. Let's just explain it on an example. We take, like we have a few machines. One machine performs not that good. So once, while it's computing its coefficients, other machines might have finished computing more batches already, more data, they process more data. So this effectively means when our machine, which is slow, will try to send the params in a naive approach, it's just gonna make the whole process not convergent because it's gonna pull the coefficients in the wrong side, right? And there could be many machines of this kind. So this gets a little bit tricky, and there again many approaches described in academic papers to solve this problem. For example, we could again do it in Windows, synchronize not every step, or we could assign weights to the received coefficients. So, for example, only the first coefficients which the PS server receives get more attention from the PS server. They have higher weight, and there are more approaches actually. Again, it's quite interesting to research this topic these days. So here on the slide, you can see two papers. On the left-hand side, there is a paper dated 2016. It's from Google. And these guys here say that actually synchronous approach worked better for them. And on the right-hand side, this paper from CERN. And these guys here say that no, synchronous approach didn't work for us. Like we use some advanced asynchronous way to help with our problems, and it was much better. So this suggests us that there is no like best way here to do it, right? And for our problem, we decided to test actually what is better. For that, we needed a framework, right? We don't want to code just ourselves. And you know that there is a distributed way of computation in TensorFlow. It's actually created for this. There's a whole page on TensorFlow documentation dedicated to this problem. There is this talk linked, and this guy discusses there all the issues with this and how to perform it. There are many articles, code samples, stuff like this available. This book is also nice. It describes parallel methods quite nicely, I think. But still, it's quite tedious to configure because you have to do it manually in TensorFlow. They work on that. Probably is going to be some more tools coming from guys TensorFlow. But currently, of course, you could use some third-party tools. But still, you need to do a lot of manual work to configure all those instances and parallel them. So we wanted to find something else. And we thought, OK, all right, so we have Spark, right? Everybody's using Spark at data science teams. It's available already. The clusters are ready and deployed. You don't need to do anything. The hardware is just there, sitting and waiting for you. And why don't we just use it to run TensorFlow? And of course, there is Yarn, which has its shortcomings as well, but it manages effectively the containers and resources and schedules our tasks. This idea is not the new one. I think if you Google this kind of frameworks, this is the first which is going to pop up in Google results, search results. It's called TensorFlow on Spark, simple as that. And this framework actually is not the oldest one. It's the first commit is made in January, I think, this year, so it's relatively new. But still, the code base there is not that clear, and the documentation needs some maintenance. So you should take a look at this if you're really curious about the problem. But I think there are better alternatives. I have to mention this framework because I have to. This framework is more like for, again, Java and Scala guys, but there are Python bindings. And it has also a mode of working on Spark. It only supports synchronization, but it works. And right, but still we didn't like it because it's more like Java-centric. It's still very stable. You could use it, but we wanted to experiment more with asynchronous synchronization. So we thought that there would be a better alternative like this framework. It's actually more oriented on Keras than on Tensorflow. It's again from CERN. It's called Keras. If you look at its GitHub page, it's not that popular. There's just 200, like almost 300 stars. But still, it's quite nice, we think. This is the author of the framework. He made almost all the commits there. His name is Jerry Hermans. I think it's his picture after he committed all those thousands of commits. But anyway, it's very well written. I highly recommend you to take a look at the code, because once you just read it for like 15 minutes, you become an expert in distributed deep learning. It implements a lot of methods. You can compare the implementations. And it has Jupyter notebooks to help you get started. It has a lot of detailed guides and references to academic papers. So that's a nice place to start. Also, there is a master thesis of this guy which discusses the same problem. Nice reading as well. And it basically works on Spark. That's what we wanted, right? So we chose this framework and how it works. Well, basically, you saw kind of this picture before. You see again PS server on top, parameter server. It works on Spark driver as a central place. And we have executors, Spark executors, which run a copy of a model. And data is quite easy to feed to these models because, well, it's Spark, you know, it's very easy. This picture I tried to illustrate here how this framework works in general. So on the left, you can see shards, replicas, partitions. I mean, partitions of the data we have. You know, it's kind of HDFS style. So we have a lot of partitions of our data. We have two partitions, for example. The trainer class does repartitioning to the number of desired workers we want to have, to the desired number of workers we want to have for our parallelism goals, right? So, and it launches those workers. They communicate with PS server. And in the end, we get a trained model. This is an example of the end user API, which you get with this framework, where you see Keras model on the top. You just can put there the model which Anton has shown, and no more changes are required. You have to feed the data in the right format because it needs some reshaping, but there are tools in this framework to assist you with that. And just these lines can train your model in parallel way on Spark cluster, assuming you have Spark context, of course, running. And yeah, simple as that. Here is this trainer class, which we just launched on the previous slide, right? It's just what I said now, just repartitions the data and then runs map partitions with index function, which is which is ubiquitous in the Spark world. You basically provide a function which should be ran on every single partition we have. So very simple, and then we just get a model from PS server, and there it is, it's trained. And the worker, actually this is a part of the code of the worker. It's quite easy to comprehend here because it just gets the data, pulls the new coefficients once in a while from the PS server, updates the current model, commits the coefficients back, and then trains on the next batch. Actually, the train on batch method is standard Keras method, so almost no magic here. Quite easy to read, right? This is a sample of the code base. So now we have the framework. We discussed all the types of parallelism, the history. We're ready, I think, to get to the test. So we didn't use clusters at our work. We just used AWS, EMR, because it's quite easy to set up, and like actually nothing needed to be set up, just launch it. We tested averaging, ADG, EA, SAGD methods. We ran it on 1, 4, and 8 machines and experimented with params, but settled on the default ones because they are quite good already, and the performance wasn't changing that much when we changed the learning rate and some other params. Well, we ran on this number of machines because obviously it's going to be too expensive to test on all the configurations, but we decided just to settle on that. The data set is a little bit different from the one you just saw. It comes from GDMC competition 2017. The dimension of the data, we made it almost the same. So like even the performance of the model is almost the same. So it's quite nice to use this one. First, let's take a look at the results on one machine and on CPU. So we took C4 for X large instance because it has comparable costs with the cost of the cluster with 8 machines. And we trained the model, this model you just saw, for around 2 hours, right? For 10 epochs. And the score was 0.958. Now let's test this Keras framework. So we took M4 X large instances with 4 cores and 16 gigabytes memory. We didn't take computer optimized instances like C4 because they are quite expensive and didn't make sense. This is a good trade-off on this instance between the memory and the CPU. Yeah, and so we tested it on 4 and 8 worker configurations. And here are the results on this graph. So in solid lines, you see the results for 8 machines. In dashed lines, you see the results for 4 machines. And the color corresponds to the type of algorithm used. So here we can clearly see that, of course, 8 worker configuration converges faster. And then it reaches just plateau and the performance doesn't change. But 4 worker configuration trains slower, but it reaches higher score. And that's what you should know about distributed learning, right? Is that basically easy does it, right? The less machines you have, the better performance you get, and vice versa. But at the same time, the degradation in performance is not that huge. So for like typical data science learning tasks, you want to get the results faster, and more machines, having more machines is better. And here we tested it on GPU on one instance. This is P2 instances and P3 instances. P3 instances are very much new. They were just released 1 week ago, I think. They have Volta GPU card, and the score is, of course, comparable. And the time it took to converge on P3 instances much faster, of course. Probably it's going to get even more fast when all the frameworks are going to get more patches and optimizations for that. And what's interesting about P2 instance is that it took almost the same time as the 8-worker CPU cluster to converge and to reach this score, which is interesting, right? So, and on this table, you can see all the results summarized here, right? And again, take a look at the 8-core, not 8-core, 8-worker machines and GPU, P2. So, of course, it's more expensive to have a cluster, but still on CPUs, on a cluster of CPUs, you can get quite nice score and quite fast, right? And basically, this takes us to this scheme, I don't know. So if you work at a company where there is a cluster, you should give it a try, obviously, because it's really fast. Before we had doubts, we thought, okay, we'd better probably just get GPUs, convince our management we need GPUs and stuff like that. But really, try distributed mode, especially if you have many machines, like, I don't know, and powerful machines, which can handle more than one Spark executor. You should really give it a try, especially with this framework, which is quite easy to set up. But if you're just a hobbyist and just want to run, I don't know, deep learning for fun, of course, your choice, it's going to be cheaper to use one GPU. And if you have extra cache, a cluster of GPU instances is your best bet, even though it's quite hard to set up on AWS because EMR doesn't support by default P2 and P3 instances. Maybe it's going to change in the future, I don't know. But at this time, you have to do all the work manually, which is, again, like too tedious. We're not a DevOps conference, right? So this brings us to this slide where we summarize the results. Again, use this keras. It's fine, it's stable. It has also some problems. It's not, doesn't have very efficient algorithm, very efficient encoding of data, which is passing between PS server and workers, as opposed to deep learning for J and the framework from Yahoo, but still it performs well. And this ADAG method in this framework was quite nice. It worked for us in most cases, right? And you should be careful with the training loss explosions, right? It's when you get not convergent data results, because we use asynchronous way of synchronization, right? It could lead to those results, but it didn't in our case.
Yes, and my part of the recommendations is just to try to use deep learning for your tasks, even for standard tasks like churn prediction. Obviously start with good problem definition. The simplest problem definition that I described might not work for you. You just have to design your own. Use keras. It's a good start for experimenting. And use recent improvements in deep learning. Use dropout, Bayes normalization, use modern optimizers like Adam. And that's it.
Okay, thank you.
And one more thing.
Ta-da!
Yeah, one more thing. If you are interested in this kind of problems and you have some experience and you just get sick of St. Petersburg climate, Polarium Krasnodar is hiring. If you are going to be a data engineer or data scientist, please send your resume to hr.team@polarium.com.
Or talk to Anton. He might hire you right now.
Yeah, thank you for the amazing talk. Good timing, and you have 15 minutes for the questions. I guess I will take one to the moderator. So, anyone questions? Let's try.
First of all, have I understood you properly that you are able to separate training input for neural network to different clusters and train layers of neural net separately on those part of data, and then join those layers into one neural net?
Does it work? Yes. Okay. So what you're describing right now is model parallelism, right?
Yeah.
When you separate the layers on different devices, right? We did nothing of that. We just took the model as it is and ran the whole thing on CPU or GPU because it's just the simplest approach. We don't want to spend our time optimizing the performance. We just did data parallelism without mixed approach.
All right.
Oh, you seem to be confused.
Yeah.
You can rephrase the question.
I didn't clearly understood. So you didn't divide training data into parts.
Training data. We divided training data, of course.
And then you joined the resulting layers into one layer.
I'm not sure how.
We use the same model, one model. We run it on each machine of the cluster for different parts of the data.
Yeah.
And we just synchronize weights of the model every X steps. So we don't have layers of the model trained on the different machines of the cluster. We train the same model on each machine, and we just synchronize average scores of average weights of the model from every machine in one parameter server.
Could you clarify how did you join the resulting? It's actually on each machine there is a separate neural network, right?
Yes.
Yeah. How did you join them into one?
Well, I think we can. Should we go? No, probably we shouldn't. So I don't know which one slide you wanna see. Well, how we join it. I mean, it's done in parallel, right? You see all these executors running, and data is fed there, and basically they communicate their params with the PS server, which is a central place where all the central coefficients are stored. And this is where the final model we get from, right? We get it from there. So we don't get the models like from each executor, we just get it from the central place where all the updated kind of synchronized coefficients are. Did it answer the question?
Yeah, so every time you do a cycle of training, you send the data to the parameter server.
Yeah.
Yeah, okay, all right. And one more question. Could you please clarify what is score in your diagram?
Score, it's a test score, it's rock curve, rock, it's rock.
Yeah.
Yeah. It's on a test data set.
Well, what does it mean? What value does it have?
Sorry?
What value, what meaning has this score?
Oh, well, okay. So we have different kind of, it's for different thresholds, you can probably explain that.
Yeah. So you have on this rock curve, on this curve, it's just, where it is? Oh, no. It's there. You have true positive rate on one axis, and then you have false positive rate on the other, and you have a kind of a probability that certain customer belongs to one category or another, and you define a threshold. For example, you define a threshold 0.1, and all the customers that has score less than 0.1, you define them as active customers. Who has more than 0.1, they left, and you just move this threshold, and you have many values of the false positive rate and true positive rate. You just draw a curve, and area under this curve called ROC. Area under this curve, it's a measure of your model performance. So the closer to the one, the better your model. Yeah. So the best model is just straight line up and then to the right.
Okay.
Is it okay? Is it clear?
Actually, I'm not 100% sure that I understand what it is, but okay.
I'm afraid I need just a bit more diagrams and more slides to explain this. Sorry.
Okay.
Well, you always can talk later, I guess.
Yeah,
no,
sure.
no one disappears everywhere. Sorry, there was a question right here. I guess no. No. Okay, so I guess you will first.
The first one I want to ask: what was the input layer size in your net?
Input layer size was, 121 feature, 92 days. So you have tensor of 121 per 92, and per each player. So you have, I used 64 customers per each batch. So as input, you have three-dimensional tensor, 64 customers, 121 feature, 92 days.
Okay, so the total number of neurons in your net?
Total number of neurons. So each RNN layer has 512 neurons, and maybe you are asking about number of parameters. It's about 2 million.
2 million. Okay, so it's kind of a lot, and you don't have a lot of data, and your score kind of impressive. Have you tested the performance of other models with?
Yes, I did, and I used also one RNN layer, and it trained faster, but it had less. It was less performant, about 0.9293, and I've decided to use 2 layers. But actually, it's not that the small amount of data.
Well, okay.
Okay.
In
It
your
depends, of course, what you call small and big. In general, of course, we have more players, we have more features, and we have longer history. But the point of this of the first part was that deep learning can be useful, but even on those kind of on this data set, it runs slowly. So you have to speed it up somehow to use it actually.
yeah, okay, but it can be interesting to see the difference between maybe logistic regression with online methods to compare.
Yeah. Yes, of course. So if this talk, the main goal of the talk was to compare results of different models, then of course I would provide you with the results for logistic regression, for XG boosting, and so on. But the main goal of that was to try to make a deep neural network distributed. That's why this was the main goal. And first part was just introductory, why you may need to use deep learning.
Okay, thank you.
Okay, another question was here, right? So let's try it.
Hi guys, thank you for the presentation. I will definitely try the distributed keras 100%. I understood the topic of your presentation was completely different, but I would point a couple of things. First one, the question, how did you validate your model? Is it that it's not overfitting? Because when I see AUC 097, I just say, no, it's just it's just feature leak or something like that. It can be like that. So did you use some kind of validation, of cross-validation? And have you actually validated against the real data? Like you predicted something and take actual after the time and how well it was predicted actually?
So about validation. On this graph you see a loss function for a training set, data set, and for validation. So orange line is validation. So you see that they are quite close, but the performance on the training set isn't that high. It is not higher a lot than validation. That's a thing that tells you that the model is not that overfitted. And this score, 0.97, it's calculated on a test set that was at the first step that was separated from the training set completely, and it was not used during training.
So it's like a holdout score.
Yes, holdout score.
Okay. Also, there was some things that say simplifying the time series.
Feature calculation.
Yeah, and what does it mean?
It means that you don't have to use 25,000 columns. You have to use 200 columns.
So so it's like not creating the lag features for the.
Yes.
How does it work?
You just feed your model with the sequences. So you calculate features daily. So, for example, you calculate feature for each customer per each day, and you feed this data as is to RNN.